So welcome everyone to this week's MCD2. This week we have Austin Tripp, and Austin is a fourth-year PhD student at Cambridge researching machine learning for molecules. His work has focused on Bayesian optimization for molecules and retrosynthesis, and he's also on the job market right now for both academic and industry positions. And today Austin is going to tell us about retrosynthesis.
Great. Thanks very much for the introduction, Emmanuel. So yeah, like you said, I'm going to be talking about retrosynthesis, specifically focusing on two works, this Python package Syntheseus and Retro-fallback, which is a paper at iClear 2024. Just like before I launch into the work, I want to say two things. Number one, if you have questions, feel free to just ask when you have them, as opposed to waiting to the end. Very happy to answer, and I have a few sort of pre-planned question breaks in the talk, just so everyone follows along. And the second thing, of course, is that everything I'm presenting is joint work. And I'd like to, in particular, thank Marvin Zegler and Jose Miguel Hernandez Lobato, who are my supervisors at Cambridge and during an internship at Microsoft, respectively, and Krzysztof Maziarz. Apologies for potentially not pronouncing that in a super Polish way, but he's also supervised me at Microsoft and really contributed to some of the technical details of the work. So everything I should say is prefaced by everything I'm going to talk about, I should preface by saying that it's, couldn't have done it without these people. So the topic of today is synthesis planning. Synthesis planning is super important to drug discovery, simply because if you want to test a molecule in any way, you obviously have to make it. If you're not familiar with synthesis planning, the general idea is pretty simple. You have a molecule you want to make, and you're going to make it using chemical reactions. So for example, usually it's thought about in the backwards direction. So you would start off with the molecule you want to make, and then think about what's the step the steps you do to get to that molecule, and then work from there. So for example, you might make this molecule by reacting these two molecules. If you can buy both of these molecules, great, you're done. Otherwise, you might need to make this molecule by, say, reacting these molecules. Maybe you'd make this molecule by reacting this molecule. And if you can buy all these molecules, you're done. And if you can't, then you keep decomposing it like this until you reach something that eventually you can buy. And if you don't reach that, then unfortunately you don't really have a synthesis plan. But this is a famously difficult problem. Not always. Sometimes you can synthesize something in a few steps and it's pretty easy, but sometimes it's much more difficult. I'll highlight two cases here just to illustrate that. So this molecule is vitamin B12. You might know it as the supplement people take. Traditionally, it has been extracted from the natural environment because it was very hard to synthesize. It was eventually synthesized, but it took about 10 years, and as apparently over 100 postdocs worked on it. So this was like a topic where papers are being published every year about getting one step closer to synthesizing it. This molecule, whose name I'm not totally sure how to pronounce, is also again structurally very complicated. People worked towards synthesizing it for 40 years. At one point, there were apparently 30 competing research groups. So it's not always easy. And I think this just sort of highlights why you might want to put a lot of effort into planning. If you think about synthesis planning as a mathematical problem, what makes it difficult is its combinatorial structure. Just abstracting away any actual molecules. Suppose you just want to synthesize some target molecule M. You might make this from any number of reactions, possibly up to hundreds, even thousands, but hundreds would be a nice typical amount of potential reactions. Each of these reactions maybe uses between 1 and at most 4 input molecules. And then each of these input molecules could itself potentially be made with hundreds of reactions. So I think from here, it's easy to see that as you grow this total search tree, the deeper it gets, the total number of nodes is going to grow exponentially. And the synthesis planning, therefore, shares the structure with other problems like chess and Go, where there's just no way to do an exhaustive search for any reasonably difficult problem, which is why you have to develop smarter techniques to allow you to search intelligently throughout the space. In my talk, I'm not really going to be able to give any overview of the work done in this space, just because there's so much of it, and there's so many different methods, and even sub-problems within retrosynthesis. But just to set the context, I'll give you a very, very high-level view of what kind of, I guess spaces kind of distinguish themselves, and which ones are popular at the moment within retrosynthesis. So the first is one-step retrosynthesis. This is just, given a molecule, predict reactions that you can perform on this molecule. This has been popular lately, especially in machine learning, because it's really amenable to deep learning. You can have a large data set of reactions that have been done, predict the products from the reactants, use your whatever your favorite GNN or transformer is, and you gotta compete for this state-of-the-art accuracy. A second area is these kind of scores people call synthesizability scores. The reason people would want to make a score like this is that often when you're designing a molecule, you just want to know, is it going to be really difficult to synthesize, or is it something manageable? Because maybe in the end, you're going to give it to an expert chemist to synthesize it rather than a computer, but you want to know in advance whether it's worth considering this molecule more seriously. And people use machine learning for this. People also design handcrafted scores, but this is kind of just a binary classification problem of sorts. And then finally, we have multi-step retrosynthesis, which is sort of what I mentioned at the beginning, explicitly try to construct synthesis plans that have multiple steps. And people use RL type methods for this, like multi-Cartload tree search, some variants of A-star with heuristics. So in this talk, I'm mostly going to be talking about this multi-step retrosynthesis with a little bit of one-step retrosynthesis. So everything I say, I guess, just bear in mind, this is not the only topic within retrosynthesis. And as I mentioned at the beginning, I'm talking about two things that I've worked on. So one is this Python library, Syntheseus, which is available on pip right now. You can type pip install Syntheseus. The main thing I want you to take away is if you work on retrosynthesis, if you need it, consider using our library. It's not really like a user-facing library, like you're not going to use it end to end. But if you're working with the methods in any more detail, I think you could find some value out of it. And the second is a more conceptual contribution. This is Retro-fallback, I think something that was just published as a paper at ICLR 2024. And the main takeaway that I would hope you can get from this is that retrosynthesis could benefit from better estimation of uncertainty because there is a lot of uncertainty. So that's kind of my intro. I guess unless there are any questions about the setup or some urgent things that are urgently unclear, we'll move on to talking about Syntheseus. So let's just say you want to run retrosynthesis or contribute another model to this space or a new algorithm. There's quite a few obstacles. So to start, you might want to train a model to say predict which reactions are going to do. And here you have a lot of potential errors. You might not split the data set in the correct way. Correct meaning like either following previous work or in a way that avoids data leakage. There's also a lot of pre-processing you need to do for this kind of data, and it's actually surprisingly easy to leave in some hints about the labels and the reactions. Things like the order in which you place the atoms can contribute a surprising amount of information. So it's actually non-trivial to just even get a trained model that has been trained on the right thing. Then you might want to evaluate your model, and maybe even just the simplest measure is how many real-life reactions does your model correctly produce. And here again, this is not so easy to judge. There's been a lot of issues with data leakage in previous papers, and the stereochemistry is this issue that is actually surprisingly hard to deal with, just because a lot of data sets don't have the stereochemistry annotated fully, and there's different works take different positions on whether you should consider stereochemistry when checking whether the reaction is correct or not, leading to results that are kind of inconsistent. So you have to just be aware of these issues. Then you might want to say use your model and run some kind of multi-step search. That's a natural extension of one of these single-step retrosynthesis model. But at least there's not a lot of great options out there for doing this. There's a few libraries that are kind of very bespoke for one kind of method, like AI Synthfinder. You can always take code from the internet and adapt it, but a lot of it's very messy and can contain some errors. So that's not an easy task. Or you can try to read the paper for these algorithms and code it yourself. But speaking from experience, there's a lot of opportunities to make mistakes there. And once you've run the search, you maybe want to analyze this and see what synthesis routes have you found. Are they any good? Do they match known synthesis routes? That sort of thing. And again, similar issues. You might take metrics from existing code, but often they're quite limited. Or maybe you want to code it yourself, but even though it's these graph enumeration problems are a little bit like undergraduate CS problems, they are a bit finicky and it's easy to make a mistake. So you might not get the right thing. So overall, from start to finish, you have a lot of potentials to either make mistakes or do things in a way that's not consistent with how previous works have done it, making these kind of comparisons you might want to see in a machine learning paper very difficult to do. We encounter these issues ourselves, which is why we made this Python package Syntheseus, which we think resolves a lot of these issues. So it doesn't provide you code to train the model. So that part you have to bring in yourself. But if you've done that, we have a standardized eval script where we've been very careful to do all the things correctly that we have noticed as mistakes in other works, and where there's just multiple different correct things to do, and you just want to know which, intentionally choose one and do that one, provide options to do all those things. For example, checking chirality, or sort of checking correctness, incorporating stereochemistry or not. If you don't want this, or if you don't want to train your own model, we also provide wrappers for a lot of pre-trained models, so you can just directly go into model eval. Instead of worrying about coding your own search, we did code these, we tested them. You can make mistakes, but the test catches the mistakes. And now we have pretty good implementations of some of the most popular algorithms, and similar for analysis. Again, possible to make mistakes, but we've written that and we've done tests, so we have some pretty good analysis code. So overall, you just don't really have to worry about all these steps, which have a lot of difficulty and a lot of potential for error. Specifically, Syntheseus provides really three things. For one-step retrosynthesis, we have baseline methods. You can put your own method, plug in your own method, and evaluate your own model. For multi-step, again, we have the baselines coded. You can evaluate your own algorithm, and you're very free to mix and match different one-step models with different combinations. So you could use, I don't know, the latest transformer model with the MCTS search algorithm which was only originally evaluated with a really old model. And in general, when designing Syntheseus, we've been quite careful to make it modular, so it's all based on classes you can extend and just depend on very dependable libraries. So it's on GitHub, it's on Pip. If you work in this kind of area, please do check it out. We hope it provides a lot of value to people, and are very happy to respond to user feedback. That's all I have to say about Syntheseus for now. Happy to answer questions on that now. Otherwise, I'll move on to retro-fallback, which is what the bulk of this talk is going to be about. So maybe I'll just quickly pause. Anyone have any questions about Syntheseus or the setup?
Yeah, I want small question. Can you go back to the previous slide?
Sure. This one.
What are Yes, like I was just wondering, what are the different evaluation algorithm or kind of multi-step search algorithm that you have implemented, and what criteria have you used to choose which one to incorporate or not?
Sorry, so you're saying which are the evaluation metrics and which are the multi-step search algorithms?
Yes.
Okay, so evaluation metrics, the main ones we have, the most popular one is basically how many reactions from the real data set were outputted by your model. Usually your model is going to output a list of reactions, and you're just checking whether the correct reaction is in that list. So like within that, the potential for errors are, if the stereochemistry is, say, not completely defined, how do you count that as correct, or do you count that as incorrect? Or if it sort of doesn't match, like people have done various things on that. So that's like one of the main things that we had standardized, or like dealing with duplicate outputs, that sort of thing. We also have support for checking whether your reaction, I guess, matches a forward reaction model, although I think the forward reaction models that are out there are not particularly good. So we have this as kind of like you can plug in your own model, but we don't really have one that we endorse specifically. That's something we're actively thinking about. And then for search, we have the retro-star algorithm and MCTS, which I'm going to actually talk about later because they're baselines for this retro-fallback paper. Does that answer your question, or have I misunderstood?
Yes, that's answer. Thank you so much.
All right. Anyone else? Otherwise, I'll go on to the second part of my talk. Great. So the tagline here is retrosynthesis with uncertainty. That was the original motivation, and I'm hoping you can kind of see this motivation through to the end. So the starting point when we're thinking about synthesis is that these synthesis plans can obviously fail. And what do I mean by fail? Well, you actually want to make the molecule. You run your algorithm, you get some synthesis plan. So presumably at some point, you'll take the synthesis plan to the lab and actually try to execute it. What can happen when you execute it? Well, it can just work. That's always a nice thing. But it could also not work quite as you intended. For example, in this particular synthesis plan, maybe reaction 2 has a very low yield, so low that you just can't even, you don't have enough mole 1A to proceed with reaction 1. Maybe reaction 3 produces a mixture, and it's really hard to separate the components of this mixture. That can be an issue, especially if the thing it's mixed with is, I don't know, is toxic and you're trying to make a drug. Then you can't have a mixture of your drug and something that's very toxic. Some of the errors are not like so sophisticated. As I said, these like reaction prediction models are sometimes just things like transformers, and they make like really weird like mistakes that are obviously wrong to a chemist, like just adding extra parts to the molecule that weren't there originally and weren't part of the reaction. So you get a lot of like nonsense stuff, although it depends on the model. But you can also have issues actually just starting the route. Maybe, for example, one of the molecules you start with is some dangerous chemical, and maybe other labs could handle it, but your lab doesn't have the equipment to handle it. Or maybe, you just go to order molecule 3 and it's out of stock, and it's going to, they're not going to update the stock for a month, and you don't have that amount of time. So there's just things that could go wrong. I don't think this should be surprising or controversial to anyone, yet somehow existing work just seems to completely ignore this. Because in papers doing proposing synthesis routes, you have metrics like the fraction solved, as if, have you found a synthesis route, you've solved it. But of course, given that synthesis routes can fail, you don't really know if just proposing a synthesis route is actually solving it. Maybe it's not going to work. So somehow there seems to be this weird imbalance between this obvious fact that they can fail and what you actually see written in papers. So when we saw this, the first thing we thought is, can we try to model uncertainty? And our takeaway is that it seems hard, so maybe not. And there's a few factors that make it hard. The biggest factor, I would say by far, is the lack of data. I mean, this is persistent with, across many fields of ML for chemistry, but with reactions in particular, what's really lacking is negative data, as in reactions that don't work, and in particular, reactions that seem like they could work. Maybe a chemist was so convinced that they might work that they actually took aside the time to try and run the reaction, and then notice that it would fail. Other things that are missing are yield data. Like yield is very important, but this is just very often not annotated, or if it is annotated, it can be very inconsistent. Sometimes you don't even write side products that appear. So in that scenario I talked about where there was a mixture, you might not even know from looking at the training data that there was a mixture of things. And finally, you just often don't even talk about the reaction conditions, so chemists might not even know how to run the reactions. Unsurprisingly, I think the lack of data, especially negative data, means there's not a lot of methods to try to predict uncertainty or predict whether reactions will fail, especially not machine learning methods. I think it's pretty understandable why this is, because if you don't have data, you can't really train a model. And even if you want to handcraft or hand engineer some kind of model based on heuristics, you don't even have data to evaluate that model. So there's just not really much you can do. And understandably, then there's not a lot of work there. And I think not a lot of work has actually led to maybe even a worse problem, which is a lack of vision. As in, not just that we don't have methods to estimate uncertainty, but actually it doesn't seem like there's an answer out there of what kind of uncertainty we would really want. Like beyond just qualitatively saying, oh yeah, we don't know what's going to happen. Like, exactly what are you going to model? Are you going to model uncertainty over yield, uncertainty over cost? Like what's the right thing to be uncertain about? And also, if you had these uncertainty estimates, I mean, what would you do with it? Are you just going to act on reactions where you're 99% certain and above? Will you just prefer reactions that are more certain? Will you try to explore uncertain reactions? Again, I think lack of sort of vision of what potentially could be done with uncertainty. So in this work, we have really mainly just focused on this last box. And what I hope to convey to you is a vision for what kind of uncertainty you could model and what you could do with the uncertainty. But I want to be transparent up front that what we have done does not really produce a convincing ML method to predict this uncertainty. And we certainly don't handle the data problem. So these are challenges, but I'm hoping that if we have a good vision for why we might want uncertainty and what we could do with it, that'll inspire people to, maybe work a bit more on ML methods, and maybe eventually inspire some people with deeper pocketbooks to try to pay for some more data annotation. So let's start here. How exactly could we describe uncertainty? I mentioned cost, I mentioned yield, but again, there's not a lot of annotation for this. So what I thought was the simplest possible way to, the simplest possible quantity to be uncertain about is just some binary quantity, like for each molecular reaction, yes or no. So I'm going to define two quantities here. The first is what I'll call a feasible function. This just takes in a reaction, outputs 1 if you consider the reaction feasible, and outputs 0 otherwise the reaction is infeasible. This could be for a whole lot of reasons, but we're not modeling those reasons. We're just saying yes or no for each reaction. Of course, though, we're uncertain about whether each reaction is feasible, and therefore, to represent this uncertainty, we're going to use a distribution over such functions, and we're going to call this distribution a feasibility model. And we're going to also now do the same thing for molecules. So, a molecule is either viable or not viable, and you have imperfect knowledge of this, and you represent your imperfect knowledge as some distribution over what this function could be. This kind of model is called a stochastic process. Probably the most famous one you would have heard of is the Gaussian process, but there's of course many other kind of stochastic processes. It's a very general model. So in particular, it includes deterministic functions. Like if you know the function, then your distribution over functions is just always that one function. It includes any function with independent randomness. So let's just say, for example, I don't know, you have some kind of neural network, and you're making some kind of probability for each reaction based off of a softmax value, something like that. You could just, if you assume that all the probabilities are independent, then that corresponds to a stochastic process just with independent realizations at each point. But most importantly, by assuming that we're modeling a stochastic process, if you want, you can take into account correlations between outcomes. And I think for reactions, correlations are probably very important because you have a lot of reactions that use similar mechanisms on similar molecules. And if you just ask a chemist, that the reason that chemists think they can predict reactions is because they know reactions that can work, that have worked in the past, maybe have worked for them, or they've seen in textbooks. And they believe that because these reactions work, that other reactions should work or other reactions will not work. So that implies there's probably some kind of correlation between dependence, and at least having a stochastic process as opposed to an individual uncertainty for each reaction could allow you to model that. So let's just assume you all buy this. At least it's the type of model we want to produce. Not considering how we actually make this model. If we consider any synthesis plan, it's pretty then simple to say under what conditions the synthesis plan is successful. So just recalling the meaning of these plans, this synthesis plan, the arrows are in reverse order because it's retrosynthesis, but really you're actually running the plan from the bottom up. So you would start by buying molecules M2 and M3, then you're performing reactions R2 and R3 to produce these molecules, and then finally you run R1. So this synthesis plan is therefore successful if you can buy molecules M2 and M3, and it's going to be successful if all of these reactions are feasible. Alternatively, if you can't buy one of the starting molecules, or even just one of the reactions does not work, then you can't run the synthesis plan, and it would then be unsuccessful. However, on the previous slide, I just said that the whole reason we're talking about we introduce these functions is that we don't know whether reactions are going to work. So you can very then naturally translate this synthesis plan being successful or not into a success probability. Sorry, I missed the slide. This is just the probability that those two molecules are viable and those three reactions are feasible. And these probabilities are with respect to functions sampled from the stochastic process. And that just very straightforwardly gives you some probability that this is going to work. So now that we've built this up, we can think about what should be the goal of retrosynthesis with uncertainty. One very natural goal would be just to find a synthesis route that's going to maximize success probability. This is pretty analogous to what previous works have done. Previous works are just trying to find any synthesis route. And now we just want to find a synthesis route that we think is going to work. And I think that's a pretty good goal, but I think you can actually do a little bit more. For example, suppose you find this synthesis route, and this is actually the best one that you can find. And it has some probability, let's say it's 70%, which is pretty good, but it's also not 100%. So ideally, you would like more. Can you do better? Well, you sort of can. If the step that you're really uncertain about is maybe this first reaction, maybe you're not sure it's going to work, and that's part of the plan. It has to work for the plan to succeed. You could potentially create a backup plan. If this reaction doesn't work, instead of doing R3, we're going to try to buy molecule M4 and do R4 instead of R3. So this is now multiple synthesis plans, with the second plan acting as a backup plan for the first plan. And by having a backup plan, you could potentially have a higher chance of succeeding in the lab than if you just go in with one maximally successful synthesis plan, because the second plan could maybe work if the first plan fails. And that brings me then to one of the key things I've proposed in this retro-fallback paper, which is I guess my recommended metric for retrosynthesis with uncertainty. And I've called it successful synthesis probability, SSP. It's a metric defined over a set of synthesis plans rather than an individual synthesis plan. And the idea is, if these are your synthesis plans, the successful synthesis probability is just the probability that at least one of these plans works. So this would be like in the lab trying this plan, and if either your first plan works, and if it doesn't work, then you try the second plan, and if that doesn't work, you try the third plan. Prudencio, I see you have your hand raised.
Yes. On the previous slide, when you proposed the reaction 4 to replace reaction 3, I was
Yeah.
wondering, like, are you thinking reaction 4 will increase the probability of success? Or just, okay, so if reaction 4 is increasing the probability of success, why is not proposed in place of reaction 3 to start with?
That's a good question. So I'm saying it increases the probability of success if your model of what's going to happen is you're going to try the first option, you're trying to try reaction 3, and then if it only doesn't work, try reaction 4. But to put some numbers on it, so let's just assume everything's independent. Let's just say reaction 3 has a 50% chance of working, and reaction 4 has a 20% chance of working. So clearly, reaction 3 is the better choice. I mean, neither are great, but reaction 3 is better. But if, in the 50% chance reaction 3 doesn't work, it's still better than nothing to have a 20% chance of trying reaction 4. That gives you basically a 10% boost to your chance of being able to, in one way or another, make molecule 1B. Does that make sense?
Yes, it does. Thank you.
Yeah. So the way I would think about this is that you have your best plan, although it doesn't necessarily need to be the best plan. But if you have your best plan, you might get some marginal or potentially even non-marginal gain by having some secondary plan. Even if it just brings you from 75% to 85%, that's still quite meaningful. It still could be the difference between executive saying this, this is too risky, let's not try to make this molecule, versus saying, yeah, let's try to do it. Yeah, and again, I think the actual probabilities will really depend on the model, and I don't really have a great answer for what the model should be. Anyways, let me go through one more slide, and then we have a bit more questions on this. So the final thing we've talked about, which is a little bit difficult, to explain, is that SSP can actually be computed in a pretty efficient way using dynamic programming. This way is going to have 3 steps. So first, for every node, we're going to calculate some success function. Just can I synthesize this molecule, including more than just the target molecule? If I could compute this, and again, putting aside how I compute this, then if I just take this function and calculate its expected value for the target molecule, that is equal to SSP, because the SSP is just the chance that you'll be able to synthesize the target molecule in any way. And finally, I can estimate this expectation just by averaging over a finite number of random functions sampled from my process. So this is the technique we're going to follow. I have this annotated. Don't read too much into this if you find it hard to follow. I hope you can just stick with me to find the general trend. We're going to start here on the left. So molecule 2, just very clearly, is only going to be be synthesizable in any way if you can buy it, because there's no reactions under it. Reaction 2 can only be executed if the reaction itself is feasible and you can successfully acquire molecule 2. And finally, you can only acquire molecule 1A in 2 ways, either by buying it or by performing reaction 2. And reaction 2 needs to be successful. You need to have all its ingredients. It's going to be the same for this branch. And then once we do that, are we going to be able to perform reaction R1? We can only perform it if the reaction itself is feasible, and we can successfully acquire molecule 1A, and we can successfully acquire molecule 1B. And we have basically the same thing if we look at this branch, and basically the same thing as we look at this branch. That's just, can we do these reactions? And finally, at the very top here, can we synthesize the target molecule? Well, there's 4 ways we could do it. It's either going to be if we can directly buy the target molecule, although usually you wouldn't be able to buy it. That's why, otherwise you wouldn't be trying to synthesize it. Or you can perform R1, or you can perform R4, or you can perform R5. So this overall success value is just the max of these. So what do I want you to take away from this? What I basically described is this bottom-up dynamic programming procedure to start from the leaf molecules and just compute whether this target molecule is synthesizable. I put here the equations from the paper, although using a very slightly different notation. Don't get too lost in it. But what I just want to convince you mainly is that you don't need to explicitly consider every synthesis plan in this tree. You can just do this pretty efficient dynamic programming solution. I'm going to do a quick recap here. So what have I introduced for retro-fallback? Well, I started from a place that I hope you can sympathize with, that we have uncertainty and we want to represent that uncertainty. I propose that we will represent that uncertainty with some stochastic processes, which are called F and B. F being feasibility, whether a reaction is going to be physically feasible, and B being viability, can we buy a molecule or not? And then we don't know these functions, so we model uncertainty with a stochastic process. So this implies that every synthesis plan, every individual plan, will have some kind of success probability, some probability of working. Naturally, you'd want synthesis plans that have a high probability of working. And if the most individually most successful plan is not sufficient, then maybe what you'd want is backup plans for the steps that won't work or might not work, or even just a completely separate backup plan. So we use this to define this successful synthesis probability, which is a metric over the set of plans. Basically, does any of the plans work? Because the chemist will take the plants to the lab and try them. So what's the chance the chemist is going to come out of the lab with the molecule, more or less? And then finally, I talked about recomputing this SSP efficiently using some recursive equations. I had a question break here, just in case people had questions. I see Kevin has a question in the chat. Can you help to explain the math expression? Kevin, which math expression were you talking about? This one in the bottom right here, or one elsewhere in the tree? Inside the box, right. Okay, well, so we have a separate equation for molecules and reactions. And the reason for that, I think, is pretty intuitive. I mean, a reaction needs everything. You can't be missing one of the ingredients. Whereas a molecule, you can synthesize it, using a number of possible ways. So I think the reaction one is a bit simpler. Basically, the reaction is feasible, and all of its children are successful. So the product, this S value is just 0 or 1. So a product of these values is going to be 1 if and only if all of the inputs are 1. So that's where the reaction one comes from. Now, the molecule one is trying to basically implement it as an OR. So you can acquire the molecule or synthesize it. It's the easiest way is just buying it. Or you can perform any of the reactions. So this max inside a max, that's like basically, the first option is buying it, and the second option is synthesizing it. And synthesizing it, you get from any of the children. So this just ends up, I could have written this in a slightly different way, I think. But it's essentially just, can you buy it or do any of the children successful? Why is step 3 using summation? So I see what you mean. Step 3 is it's not really using summation, it's using averaging, right? So you have this binary quantity, and maybe, I don't know, in 70% of the times it's 0, and 30% it's 1. In that case, you sum them up, you get a sum of 30, divide by 100, and you get 0.3, which is your estimate of the probability that it's going to be 1. Does that make sense? Great. Any other questions about this? Is there any way of describing models' uncertainty about uncertainty? I'm actually not really sure that there's like even a way to talk about uncertainty, just because if you have, let's just say you have some distribution, I don't know, like what's the probability that it's going to work, but you're uncertain about what that probability value is. You can always integrate out this second level of uncertainty, and that implies a first level of uncertainty. So it's not really clear that like provides any kind of additional kind of uncertainty in that way. But yes, I guess like alternatively, you could imagine doing some experiments during the planning to reduce the uncertainty. I'm not sure. Does that answer your question at all? If not, we can talk about it more at the end. I see what you mean. Yeah, there might be steps where you might want to ask a real chemist to try it. Yeah, let's table it for later. Okay. Any other questions just about this general procedure here? It's not critical that you understand everything. You don't have to write down the equations. I think what's important is just the motivation and this kind of rough recursive procedure.
Can you go back to the previous slide quickly?
Sure.
I was wondering how you get the probability of the reaction.
Okay, so the main answer is that we were assuming that you have this feasibility model, some distribution over whether reactions would work. So for the purposes of this computation, you say you sample a set of outcomes from this distribution, and then that's what you're using this computation for. But I guess you might want to ask, what would this model look like? And I don't have a great answer for like how to build a really realistic model, but just mathematically, it could be like a Bayesian neural network. It could be a non-Bayesian neural network that just assigns a probability to each reaction, and you assume everything's independent. It could be like a Gaussian process model. I tried 2 of these in experiments I'll talk about later. Does that clarify anything?
Yes, thank you.
Okay. Let's move on to the key algorithm here. I have a little bit less time than I expected, or I've been presenting a bit slower than expected, I think. So I might skip over some of the details of this. I think they're not they're not super easy to explain anyways, and maybe not so relevant if you just care about the algorithm at a high level. So if we suppose you're convinced about this SSP metric, naturally you might want to design an algorithm or use an algorithm to try to maximize this SSP. So could you use an existing algorithm? Well, kind of, but it's a bit difficult. Previous algorithms like Monte Carlo tree search or RetroStar, they have these like reward functions and cost functions, and they give rewards and costs to individual synthesis plans. However, this SSP I've talked about is something that inherently depends on multiple synthesis plans because you're considering any one of a number of synthesis plans working. You could set these algorithms up to try to produce plans which are individually successful and hope that will result in a high SSP, and it might, but it's not necessarily going to be the case. I have an example here which I hope gives an intuitive flavor of why this is. So this is a tree. Let me take the number away. This is a tree. I just colored the nodes red and green. Think of green as there's some synthesis plan with a non-zero probability, and red meaning there's no probability 0. We haven't found any synthesis plan. So essentially, we found one potential synthesis plan via M2, and then we have these 2 other branches which we could explore further and maybe find another synthesis plan. So the question for an algorithm is, should we look at M4 or should we look at M3? And what I hope it becomes clear is that you can't really answer this without considering the synthesis route you've already found. So let's say, for example, the probability that this reaction 2 is feasible is 99%. In this case, if we explore M3 more and try to produce a synthesis route, that will actually only be useful in the event that this reaction 2 is not feasible. But we've said we believe it's 99% feasible, so this is just very unlikely to happen. So these extra synthesis routes are just not really going to contribute much. So in this case, it probably makes sense to expand M4 and try to produce some other synthesis route that's going to, say, be successful if reaction 1 didn't work. Alternatively, if reaction 2 only works 1% of the time, then this potential synthesis route we found is probably really unlikely to work in practice, maybe 1%, and therefore maybe expanding M3 would actually be a good choice. So it's going to depend, I guess, on the numbers of like maybe M4, maybe R4 is even worse. But intuitively, it seems like you can't reason about how to improve this SSP without knowing like which the set of synthesis plans you've found so far. It's not just something you can reason about by just looking at one individual synthesis plan. So this motivates retro-fallback. We've designed a greedy algorithm that's specifically trying to maximize SSP. It's a little bit complicated, so I'm hoping I can give you the intuition and like the gist of it in this talk. But I think for the full details, you need to look at the paper. The algorithm is a greedy algorithm, so pretty much at each step, it's going to first try to calculate how each leaf node could potentially improve this SSP. And then it's going to pick the leaf node that it expects has the highest improvement to SSP, and then go back to step 1. So it just does this over and over again. Now, how is it going to estimate this improvement? Without getting into the details right now, at a very high level, it's going to use samples. Just like we use these samples to estimate, whether a molecule is synthesizable with dynamic programming, we're going to be doing something very similar. Using dynamic programming, and then we're going to average over the samples to get some kind of average output. Okay, so the starting point then for how different expansions could affect the graph would be to predict what would actually be the effect of expanding each leaf node on the leaf node itself. And we're going to use a heuristic for this. So there's really 2 outcomes. If you expand a node, either you're going to produce a synthesis route for it, or you won't. And by producing a synthesis route for it, specifically, I mean, just say you expand M2, just producing a synthesis for M2. I'm not talking about extending that into a full synthesis route for MT, but just can you synthesize this molecule at the very bottom of the tree? We're going to, introduce this heuristic, and we're going to say that if the heuristic value is P, that implies we believe that expanding this will produce a synthesis route for that molecule with probability P. So higher P means more likely to succeed. Okay, with this, we can revisit the graph from a few slides ago and kind of just see what implication these predictions would have on the graph as a whole. At a high level, we're going to do this. We're going to define this function I've called psi, and you can interpret psi as the probability that you're going to get a successful synthesis plan for this node if you assume you also get to do an expansion of a node. So I'm going to add a few labels to this graph, but just intuitively note that we're assuming here we can't buy any of the molecules, so there's no synthesis route now, and that all of the reactions, except for R5 here on the right, are feasible. So R5 is the only reaction that doesn't work. Let's start in the middle here. So molecule 4 is not viable, you can't make it, but we say we have a heuristic value of 50%, so potentially we can make it with 50% chance. That will translate up to this reaction. Again, we can't do the reaction now, but since we believe we can do molecule 4 with 50% chance, then 50% chance we can also do reaction 4. We're going to do a similar thing here with molecule 5A and 5B, although the heuristic value is slightly different. But in this particular case, this reaction 5 is infeasible. So no matter what kind of synthesis plans you get for its input reactions, nothing's going to come of this. So there's no potential improvement here. Finally, for this branch, again, we just kind of made up some heuristic values. Let's just say 0.9, 0.9, 0.9. So this is all you currently no synthesis route, but you think 90% chance you can get one for M2, and similar for M3. But at R1, recall that it has just 2 reactions. If we expand something on the left branch, then we won't have anything on the won't have any synthesis route on the right branch, and vice versa. So this actually would have 0 predicted improvement. So then we can carry these up at the top. You see there's 3 options. There's a potential improvement of 0 from the left branch, potential improvement of 0.5 from the middle branch, and 0 from the right branch. So obviously then this middle branch is looking best, and maybe that's what you would expand. This obviously is a bit suboptimal because you kind of realize that no matter how promising these things in the left branch seem, you're never going to end up visiting them if you do this algorithm. So that's why this is not actually the algorithm we do. We do a very slightly changed version of this. So instead of expanding a single node, we're going to say we get to expand a single synthesis plan, meaning for every reaction, we do 1 expansion for every child, potentially. So this changes things. In this particular graph, it's going to just change things for R1. So here's all the numbers from the previous slide. They're all the same, so don't have to check them too carefully. The key one that's different here is now our potential improvement for R1 is going to be 0.9 improvement from 90% chance of making the left molecule times 90% chance of making the right molecule, bringing us now not 0, but 81%. And this means actually that with this modification, the most promising synthesis route looks like it's this left synthesis route. And more generally, I have a set of recursive equations. I think they're explained in a bit more detail in the paper, but it's something that looks a lot like a success calculation. It's just that now we're using this heuristic so much. So hopefully, this is not quite the full algorithm yet, but hopefully I've just conveyed the idea that using a very similar procedure to just checking whether there is a synthesis route, you can also check, whether there is a potential synthesis route, or what's the probability that there's a potential synthesis route if you make some kind of change. I'm going to do two more slides, and then I think we can talk about questions of the algorithm. So now that we've done this, it's time to select a node. We're going to introduce this another function, which is as a little bit like the previous one, but instead of the chance you can synthesize sort of a particular node with an expansion, this is the best synthesis plan for the target molecule, specifically which the node belongs to. So for the very top node, we found the synthesis route with an 81% chance of working. And without getting into labeling every node, basically, this left branch we just talked about, this is the branch we get 81%. Here we get a 50% branch, and this was the 0 branch, and therefore maybe we would choose this 81% branch. But recall that this is all done for one particular sample of F and one particular sample of B. But these are quantities we're uncertain about. We're going to be averaging over them. So if we complete this multiple times with different samples, it might actually be the case that this 81% route on the left is actually not the best choice, because maybe there's a decent chance that one of the reactions doesn't work, and maybe the best choice might actually be one of these other reactions that has a suboptimal score, in each instance, but is sort of on average the highest one. So I'm just saying this is to explain why we're trying to calculate something for every node as opposed to just looking at the particular best node. Okay, final scenario. Consider this graph again, but now just think about what if we make one change. So everything's the same except for this middle branch. In this middle branch, we're saying now actually we can buy this molecule, which means we can run this reaction, which means actually we can make the target molecule. In this particular case, no matter what we expand, it's not going to change our successful synthesis probability. And the reason is that this probability is like, what's the chance, averaged among all outcomes, that any synthesis route works. So if one synthesis route works, then you don't really need a second one. So you're kind of only going to improve this by considering cases where you do not have a synthesis route already. And this is what basically leads to our final algorithm. We're more or less going to choose nodes based on this criteria here. This is a little bit hard to interpret, but roughly it's just you're averaging this row value, which I kind of introduced heuristically on like 2 slides ago, but you're only considering cases where you do not yet have a synthesis route. And the algorithm is basically just computing something for all nodes and picking the value with the best improvement. So to do a quick recap of this, because I know this is probably a lot, we talked about how a node could potentially improve this. We introduced a heuristic. For this whole graph, we introduced this function of how much you could potentially improve it. We propagated this back down to all the leaf nodes. We computed this average effect, and now we're expanding the node with the highest probability. I had arranged here to do questions about retro-fallback, but I realized actually we're kind of close to finishing. So I wonder if it's actually worth me skipping over the next section, basically just concluding here for questions. I don't know, unless people feel like they don't have any questions.
The audience, I guess. See any questions?
Let me go. So let me go for one more minute. I'll just like I think the details of this are not, they're not critical because these are online. You can see it in the paper. So we did some experiments. The key difficulty being that, as I said at the beginning, I don't think we have this model that tells you how uncertain to be. So it's not like we can test, I don't know, test retro-fallback in the real world with real world models. So I had to kind of make up a model. I did, I tried to do a decent job. But kind of the overall caveat to all these experiments is that this is just done with the best model I could make up. We tested against some baselines, tried really hard to set the algorithms up in a fair way, because it's, these algorithms themselves have tons of parameters, so how can you really compare them fairly? And the key result really is this, that when we just look at the average successful synthesis probability across a bunch of molecules, retro-fallback seems to be better than these baselines, which is kind of what we'd expect because we designed it specifically to maximize this one metric. In conclusion today, I basically told you about 2 things: the Syntheseus package, hopefully, if you work in the space, you want to check it out. I think it could be very useful for people. And retro-fallback, which is this algorithm starting from the motivation of wanting uncertainty and trying to sketch out a vision of what we could do with this uncertainty. And this is hopefully, hopefully, if you have these models, you can produce a set of synthesis plans that has a decent chance of working. And if you want the details, it's currently on open review for iClear, so you can just check that out. And in the future, I hope people can work more on these models and try to improve evaluation for retrosynthesis. It seems like an area that really needs the help. And that was essentially what I wanted to say in the talk. Thank you so much for listening, and I'm really happy to have questions and discussions now.
Great. Thank you for the talk. I have some questions, but maybe the audience also have had a discussion that they wanted to follow up on. If you want to start with that. But I can ask a question first. I guess,
Sounds good.
where do you see things evolving as like more and more ML, let's say, enters the kind of search learning to search and all of that? Do you think we'll continue to need these search methods like what you develop versus like, conditioning the model on like, here's what's currently viable, here's like the current set of reactions that our labs can do, go forth. Presumably as ML gets better, like these models will generalize better and learn faster. And because of the conditioning, then there's no relearning necessary.
I don't think I really have a good answer for that question. To be honest, I don't feel like I'm an expert on these like single step models. Maybe just two things that pop into mind. It doesn't seem likely that you can just give a model, here's all the reactions you can do, just because there's so many reactions you can do. Like not just reaction classes. I mean, there's a huge amount of reaction classes, but obviously it's kind of depends for each molecule which reactions in the class you're going to be able to do. So, I mean, it certainly can't rule out like giving a language model, a task, and it provides a synthesis plan. In fact, I think there was actually a demonstration of that for like, I think it was called ChemCrow, or they kind of made a synthesis plan with an LLM. But obviously that's way more feasible for shorter synthesis plans, and longer ones. I think nothing kind of works. My impression is nothing kind of works for longer ones, so it's unclear how that's going to evolve. I'd be surprised if there was like no explicit search in the future.
Yeah,
but who knows?
Well, I guess another question is, where do you see the role of, say, more physics-based model in providing us things like yields and uncertainties? And as you get, let's say, more quantities, how hard is that going to be to fold into?
That's another really good
search
question.
methods?
I mean, so definitely something outside my expertise, but from what I have heard, talking to people who are experts in these physics models, it's really hard to model reactions because they're all using excited electronic states, and kind of the best methods we have, things like DFT, are for ground states really, and the sort of excited state variants, so people say, are just not as good. So I think that means it's hard, and generally anything that's providing better information in physics is going to be expensive. But that being said, it's probably not, it's probably still way less expensive than actually going to the lab and doing it. So I could see a synthesis planning procedure that is maybe making some calls to a physics model to get some information. But this would be a much more involved system than just like, something that you could run on a laptop or a single computer, I would think. But I think that's a really interesting direction to pursue. Like that would be a way to reduce uncertainty about that, especially if for certain reaction classes you think you can do a decent simulation.
How's that?
I think that that question kind of leads into what I was asking pretty well, and that if there is some sort of ground truth that a search algorithm could refer to, I think it might, make the search process that you described in retrosynthesis a lot better, but also like it could train on data that it knows it specifically needs. And so I was curious about like whether that was something either you or any of your collaborators were looking into.
I mean, I think it's an idea that's been talked about. I hadn't personally looked into it, and I think that's mostly just because it's not really in my field of expertise. Like in terms of there's not huge troves of offline data that we could just leverage and query at runtime, and things like physics-based simulations take a lot of care to set up. So that's why I haven't personally looked at this, but I think it would be a really promising direction for people to look at. Like that would be, absent you being able to actually do an experiment, I think using querying literature or getting some information from somewhere is probably the next best thing.
It does definitely seem hard. I don't want to at all minimize that. I think like for estimating the probabilities of reactions going forward, you would either need to hire a chemist to do it or a very expensive physics simulation, like you said. But I think for the viability metric that you introduced, that might actually be a thing. Like, if you trade an agent to just go scour any of the online markets, like you might be able to get a better estimate of that.
Oh yeah, that was something I didn't say explicitly, but maybe we should have. I think there's a huge difference between feasibility and viability. Like this viability, I think most things actually you basically know whether you can buy them. And there's like some edge cases, there's delays, or I don't know, or like there's these virtual libraries of molecules that they might not be able to sell you everything. But you have a lot more certainty about that, whereas the reaction one is way harder to model. So yeah, but that being said, though, I think like there is something more that could be done with the reaction model. Even just like say, well, first of all, you could kind of include reactions in the training data set. And if a reaction proposed is actually in a training data set, then you could probably be very certain about that one reaction. So, and this does come up, like maybe the exact reaction was used before, and that would be good to know. And then beyond that, you could probably do something like checking if it's really similar to a training reaction or a reaction in the training set. So something like that. So I think it's not that there's I think there are things between nothing and something really complex with physics simulations that could be tried, but as I understand, have not really yet been tried.
Okay, that sounds really cool.
Yeah, but I think if you guys work on retrosynthesis, if you think this is interesting, I think this could be an interesting area for future work. Like as I said at the beginning, what I hope I could convey with retro-fallback is like there's something cool you could do with uncertainty. You could like make a set of plans and backup plans, and that is maybe a reason to look more seriously into seeing how you could create uncertainty estimates.